Welcome back to this next video in the playlist on Galois theory. So in this video we're ready to prove one of the two theorems that we needed in the video on solvability by radicals. Namely, we're ready to prove that if you have a characteristic zero field and you have a radical extension of that characteristic zero field, that radical extension is always contained inside some larger extension of your original ground field that is finite solvable. So radical is always contained inside finite solvable is the title for this video, in the case of characteristic zero fields. And if you remember, we used this in that video on solvability by radicals to get Galois' characterization of when a polynomial is solvable by radicals over a characteristic zero field. So let's crack on with proving this. So now that we've studied cyclotomic extensions, solvable extensions, and Kummer extensions, this is actually quite easy. It's quite beautiful. So we have a characteristic zero field here there. So characteristic of f is equal to 0. And we have a radical extension of it here, r. And I now need to show that for this arbitrary radical extension of f, that it's contained inside some larger extension of f, which is finite solvable. And I'm going to build that for you. I'm going to overtly show you how to construct such an extension. So finite solvable extensions are automatically finite Galois because to be solvable you have to be Galois with solvable Galois group. So a starting point would be to show that R is contained inside a finite Galois extension, and then we'll try and improve that to finite solvable. R is not necessarily a finite Galois extension itself, so we're going to get a bigger extension that is going to be finite Galois. So how do we do this? Well, R being a radical extension means that it's achieved by joining on a successive or a finite number of radicals. It's built out of a finite number of simple radical extensions. So R overall is a finite extension of F. So this extension here is finite. Finite extensions are always algebraic, and then because we're in characteristic zero fields are all perfect, so any algebraic extension is automatically a separable extension. So I can conclude that R over F is a finite separable extension. If you have a finite separable extension, there's two incredible things that hold true. One is that it has a Galois closure, and two is that the primitive elements theorem holds true. Let's start with the fact that it has a Galois closure. So a Galois closure means that it sits inside a larger extension that is a Galois extension, in this case a finite Galois extension, and which is the smallest Galois extension that contains your starting extension. So there's no standard notation that I know for Galois closure, so I've just made up my own. So GC for Galois closure, and then it's the Galois closure of the extension R over the base field F. So this means the smallest extension of F, which is a Galois extension, which contains the extension R. That's what is meant by Galois closure. I might just write that down in case. Hopefully you have come across this concept in more basic Galois theory courses. In the first course in Galois theory. So this is the notation I'm using. So because the extension is finite separable, I can construct its Galois closure. I can overtly now say what the structure of this Galois closure is, and I'm going to use the primitive element theorem to simplify things. So the primitive element theorem says that if you have a finite separable extension, and I have no intention of proving the primitive element theorem in this video. This program used to be really good, whereas now I end up clicking things accidentally and then opening new pages and ruining my flow. Anyway, so the primitive element theorem, which we'll abbreviate to PET, this says that if you have any finite separable extension, that extension is simple. So in particular, there is an element alpha in R such that R is equal to F adjoint alpha. That is not a trivial theorem. That needs proving. It's not too difficult to prove, but we're not going to do it here. I'm going to assume you know it. So finite separable extensions, they have a primitive element, they are always simple. It doesn't need it to be a characteristic zero base field. Any finite separable extension this holds for. But we're using that fact here. And now we can spell out nice and concretely what the Galois closure of R over F is. So you can say it will be the splitting field over F of the minimal polynomial for this primitive element alpha over F, like so. That polynomial there is going to be irreducible. It's a minimal polynomial, ergo it's irreducible over F. And because we're characteristic 0, then all, again, it's perfect, and therefore all irreducible polynomials are separable, so that's a separable polynomial. So this splitting field is therefore going to be a finite Galois extension, and it's going to be the smallest finite Galois extension containing R, because any finite Galois extension that contains R is going to have to contain alpha, and any finite Galois extension that contains alpha is going to have to contain the splitting field of the minimal polynomial for alpha, because it's normal. Finite Galois extensions are finite, and then Galois, which is normal and separable. So this is a finite Galois extension, and it has to be the smallest one that contains R. So that's a concrete realization, if you like, of what this Galois closure is. So good. I have now proven that my original radical extension is contained inside a larger extension that is finite Galois over F. Where next? Well, I want to now convince you that this extension here is actually still radical. So as well as being finite Galois, which I'll just abbreviate to FG, it's also still radical. How do I convince you of that? It's because if you think about the Galois group now, and I'll just call this Galois closure just so that I don't have to write too much, I'll just call it K. If I think about the Galois group of K over F, this is going to contain a bunch of automorphisms that are going to fix F, and they're going to alter R. R is not going to be mapped to itself by these automorphisms. They're going to move R onto different isomorphic subfields, copies of itself that are contained inside K. So, if I take, for example, sigma, and let's say sigma is a non-identity element of the Galois group, then the degree of this extension here, or let me just think a moment. No, I won't say that. That would be wrong. So it's not necessarily true that all of the automorphisms are going to move R. Some of them might fix R, but some of them definitely are going to move it. And if you think about what the images of R, so if I go over all of the automorphisms in the Galois group, so if I take sigma of R, and I let this vary over all of the elements of the Galois group, then I'm going to get lots of different subfields of K, the Galois closure of R over F, and they'll all be contained inside here. They'll all be isomorphic to R because of the fact that these are field automorphisms, so they have to map R onto something that's isomorphic to it. But they aren't equal to it. They are different subfields inside K, some of them. Some sigmas might map R exactly onto itself and just fix it. The identity one will certainly do that, but some of them won't. How do I know that some of them won't? It's because, again, this comes down to the core idea of Galois theory, which again is that the Galois conjugates of alpha under the elements of the Galois group of the splitting field of the minimal polynomial for alpha over F, the Galois conjugates of alpha have to be the other things in its minimal polynomial. So, if I look at where alpha is being mapped to by all of the elements of the Galois group, it's going to be mapped onto loads of other things that are the other roots of this polynomial. So you'll be getting, if we call alpha's Galois conjugates, we'll call it alpha 1. So let alpha equal alpha 1, and then you'll have alpha 2 all the way up to alpha n, let's say, where n is the degree of its minimal polynomial. So you have these other roots of the minimal polynomial, its Galois conjugates, and if you go over all of the elements of the Galois group, you're going to have to hit all of these. So the orbit of alpha under the action of the Galois group has to equal all of these other roots of the minimal polynomial. So this will give us other subfields inside here. It will give us f adjoin alpha 2, for example, here, f adjoin alpha 3 here, maybe, etc. These are the other copies, isomorphic copies of R that R is going to be mapped onto by elements of the Galois group. Now, they're all isomorphic, so they're all still radical extensions. F adjoin alpha 2, F adjoin alpha 3, all the way up to F adjoin alpha n. They're all radical extensions. And the Galois closure of R over F is then going to be the compositum of all of these. So it's going to be the compositum of R with all of its images. I don't really know how best to write this. So you would want all of its images. So let's say just like R prime, R double prime, maybe this is just notation that I'm making up. All of these isomorphic copies of R that it's being mapped onto, the compositum of all of them will give you the Galois closure because of the fact that if you go over all of these, they're going to contain all of these other roots of the minimal polynomial. Therefore, this compositum is going to contain all of the roots of the minimal polynomial, ergo it's forced to be this whole splitting field of that minimal polynomial. And then we know from our study of radical extensions that the compositum of a finite number of radical extensions is still a radical extension. And that then is my argument as to why the Galois closure here, again, I've clicked things that I didn't mean to click. Why the Galois closure of R over F is forced to still be a radical extension, because it's the compositum of all of these images of R under the elements of the Galois group of K over F. And that compositum, those things that we're compositing together, are all still radical extensions, and together they make the entire thing. And there's a finite number of them, so it's a compositum of a finite number of radical extensions. Excellent. So I've now got that R is contained inside this larger extension, the Galois closure, that is a finite radical Galois extension. So that's good. Now what? So let's draw a new picture. So we've got F here, we've got our radical extension here, R, and we've got K here, which is the Galois closure of R over F. And I've said that K over F is a finite radical Galois extension. So because it's still a radical extension, I can therefore write it as F adjoin alpha 1. And now these alphas are different. Oh, I should probably use a different letter because otherwise it's confusing. So F adjoin beta 1, let's say, F adjoin beta 2, all the way up to some beta, let's say L. So because it's a radical extension, it is built out of a finite number of successive simple radical extensions, and this is what I've got here. So I'm saying that beta I to the power of some ni is going to be an element of F adjoin beta 1, beta 2, all the way up to beta I minus 1. This is just the condition for this being a radical extension. So there are loads of mini extensions here, which is F adjoin beta 1, F adjoin beta 1, beta 2, etc., where each of these little extensions is a simple radical extension, and them on top of one another makes the full radical extension. And we have that each one of them has this letter, or this natural number, ni, associated with it. Now what I'm going to do, so I'm now, just to spell out where we're going, this is not good enough, what we've got so far. We've got a finite radical Galois extension. That's not what we want. We want a finite solvable extension. So we're trying now to create a bigger extension that is going to be a finite solvable extension. How are we going to do that? Well, you might like to have a go at doing this yourself. Remember, in the video on finite solvable extensions, we showed that a finite solvable extension is a finite Galois extension that is built out of a finite tower of abelian extensions. So I need to try and make some finite Galois extension that is built out of a tower of abelian extensions. At the moment, I've got a finite Galois extension that's built out of a tower of simple radical extensions. Those aren't necessarily abelian. However, Kummer extensions I know are abelian because they're cyclic. I also know cyclotomic extensions are abelian. So that's how I'm going to do this. I want to convert all of these simple radical extensions, I want to convert them all into Kummer extensions, because then they'd all be abelian and I'd be in business. How am I going to do that? Well, I need to put on all the necessary roots of unity. So what I'm going to do is I'm going to define my overall n to be n1 times n2 all the way up to nl. So I'm going to make n divisible by all the necessary ni's for these betas here. Okay, and what I'm now going to do is I'm going to create the nth cyclotomic extension of f. I can do that. That will be a abelian extension. So it'll be finite Galois with abelian Galois group. Now, again, I'm going to use a fact that I hope you're familiar with from more basic Galois theory, which is that if you take the compositum of two finite Galois extensions, you get another finite Galois extension. So I'm now going to take the compositum of K, my Galois closure of the radical extension over F, and the nth cyclotomic extension of F. And this is still going to be a finite Galois extension of F. So this extension, K compositum Fn, this is a finite Galois extension of F here. Excellent. This, I claim, is going to be the extension I need. This is going to be my finite solvable extension. I now just need to prove it. I know this extension here, this is an abelian extension. So what I now need to do is try and make a tower in between these two here of abelian extensions, and then I'd be done, because I know the overall thing is finite Galois. Just to say again, I'm assuming you know this fact from more basic group theory, which is that the compositum of two finite Galois extensions is still a finite Galois extension. There's more to it, you know. You can actually make a comment about what the Galois group of such an extension is. We don't need that more advanced part here. We just need to know that it's finite Galois. So we're now going to use another sort of fancy bit of Galois theory, or basic Galois theory, which is that you can translate extensions. You can translate... well, actually, no, we're not going to... No, ignore me. We're not... This is more... We are going to translate extensions, but we're not going to use the fact that they're going to remain Galois, because they're not necessarily Galois. So we're now going to translate these simple radical extensions. So I'm now going to say, okay, what is the compositum? Oh, what am I doing here? Sorry, again, I'm clicking things... It's clicking things for me that I don't think I'm clicking. So what is this extension? This is going to be the nth cyclotomic extension adjoin beta 1, beta 2, all the way up to beta L. If you join all of them on, then you get the whole of K. So this is what this compositum is equal to. So it's therefore got a whole bunch of mini sub-extensions here. You've got the nth cyclotomic extension of F adjoin beta 1. Then it goes up to the nth cyclotomic extension of F adjoin beta 1, beta 2. And then we go on, and it goes up all the way to the final one, which I won't try and squeeze. Oh, actually, I will. The nth cyclotomic extension of F adjoin beta 1, beta 2, all the way up to beta L, like that. Okay. Now, here's the brilliance now that... You know, what are we doing here? What are each of these extensions going to become? They're going to become Kummer extensions, because what are you doing here? You're adjoining on something that is a root of x to the n1 so we know beta 1 to the power of n1 is an element of f, so it's certainly an element of fn. So you're adjoining on some polynomial of the form, you're adjoining on a root of the polynomial of the form x to the n1 minus some a, where a is in the base field. And you're doing that onto a base field that contains a primitive n1th root of unity, because it contains a primitive nth root of unity, and therefore and n was constructed so that it had all of these ni's in. So it's certainly going to contain a primitive n1th root of unity. Just take the primitive nth root of unity and do it to the power. So if we have zeta n is the primitive nth root of unity, do that to the power of n2, n3, all the way up to nl. That will then be a primitive n1th root of unity. So therefore, the moment you've got one of these, you're going to have all of them. So you're basically taking the splitting field of a polynomial of this form. You're going to have all of them because you've got the primitive n-1th root of unity here. So you can just multiply by powers of this to get other ones. I'm assuming, of course, that none of these betas were 0, because why on earth would they have been 0? You wouldn't be joining 0 on. 0 is already in the base field. If any of them were 0, you'd just get rid of them and then have a shorter list. So multiplying by the different powers of the primitive n-1th root of unity are therefore going to give you the different roots. So you're taking the splitting field of a polynomial of this form, and we know that from our study of Kummer extensions that gives you a Kummer extension. So this is going to be a Kummer extension. And then the same argument holds up here. You know, this extension here that we're taking an extension of is going to contain a primitive n2th root of unity, and we're then joining on a root of a polynomial of the form x to the n2 minus a, where a is certainly going to be in this base field. I mean, it's actually going to be in a much smaller field than this, but it's certainly going to be in this one. So each one of these is going to become a Kummer extension, and we know Kummer extensions are all abelian. So we've now got this tower of abelian extensions, this finite tower of abelian extensions inside our overall finite Galois extension, and therefore by our study of solvable extensions in a previous video in this playlist, we can conclude that this, and I might change color even for this here is a solvable extension of this, and it certainly contains R here, so it is a larger extension of R, a super extension of R if you like, that is finite solvable over F. And that's what we wanted to do. We started with an arbitrary radical extension of a characteristic zero field, and we proved that it's contained inside a larger finite solvable extension. So we'll call it there. Thank you very much for watching. Oh, I hate